Okay, first thank you the organizers to invite me. It's my great pleasure to be here. Also to say a few words about Misha. So I met him probably more than 20 years ago in Netherlands. At that time, it was a couple of years after my PhD. Michel was editor of European Journal of Combinatorics. I gave him the paper to submit to his journal, and I realized immediately that he's a different person than usual. Very strict, immediately checked the paper, and he said, "You're the beginner." I said, "Why am I the beginner?" He checked the references, and they weren't written the way as they were supposed to in that journal, and so on. So it was interesting. It reminded me a little bit about my father. Later, I learned that they both had to leave their country and live in another country. Only Michel went to France. My father went from Serbia to Slovenia. But it was an interesting story. So slowly I start meeting Misha at various places, Korea, Japan, and I can say we became close friends. I even hosted him very shortly in Ljubljana. So it was very nice, and really liked the enthusiasm because some people do mathematics to have a better life, or I don't know, to make a career. But with him it's rather the other way around. He lives to work, he lived to work, to do mathematics. And that was evident that he was keen on mathematics, but he wanted to have also a balanced life, like my students say these days. And I say, yes, you have to balance life, but first you put your corners, and then you go from there on. And Michel knew how to do that. Okay, so I don't have joint work with him, so maybe you can flip to my talk. But definitely the flavor of my talk will follow the content of a European journal. Michel was glad to accept my papers, and I will try to stay honest and as much combinatorial as possible. I won't get into any. I'll try to stay away from heavy mathematics, and I'll show you just combinatorics, counting, double counting, then a little bit of finite geometry, how we say, konačna geometria. Where is your microphone? Help me, help. Konačna geometria? Yeah. Okay, so when I was finishing my undergraduate degree, I was pretty much involved in topology, and somebody gave me a Russian book, Очевидная topologia, and by Efremovich and Boltyansky, and they said that for the soul of mathematician, fight I think the angel of geometry and the devil of algebra. That's how it was written. And of course I thought, well, you can change these things, you never know. A while later, I realized that there is not so much difference between geometry and algebra, especially in the finite case. These things get very much entangled and overlapping. So, for example, it was Hilbert saying that, say you study geometry, you have points and lines, so most of the time we will use these symbols, points and lines. Doesn't matter. I won't go that far. Okay. So Hilbert said that in geometry what you want is that every point looks the same as any other point, that every line looks the same as any other line, which means really that there is an automorphism of the space which maps one point to another point. That's what we think in Euclidean geometry. Of course, in finite geometry may be different, but the thing is that you can start thinking about symmetry, about the groups, and then maybe the geometry and algebra are not that different. But you will see in our case, we will stay as much as possible away from geometry and do only combinatorial things. So in our case, we'll work with graphs. So the graph will have vertices and edges. So how do you say vertices?
Вершины и ребра.
Yeah, and rебra. So, okay, so, and our mapping will be the mapping that preserves the adjacency. Okay, so this is our object, and I would like that every vertex looks the same as any other vertex, just locally. And that means that when I look the number of neighbors, it's the same for every vertex. So when I write here the circle around every vertex, this disk looks like the same thing. But I will impose more structure. So, for example, I will want that every edge lies in fixed number of triangles. And also, if two vertices are not adjacent, I want that they have in common fixed number, and I'll denote this number with mu of common neighbors. So you can consider graph as точка or vertex, then the neighbors, susedi, and then the non-neighbors. And so the number of triangles, it's really the valency on the neighborhood, on the susedi. So what is the valency in the neighborhood? While this mu, which is intersection of two spheres, the same way as in this case, only in this case we started with two adjacent vertices. Here we started with two vertices that are not adjacent. That's the only thing. So we have three parameters in our graph. So parameters are k, lambda, and mu. We could add maybe also the number of all vertices. But it turns out that you can do the counting. The counting goes between those two bubbles, and you determine what is the... So, this is the neighborhood, so the size of this neighborhood is k. This is the non-neighborhood, or in the complement, you could say that this is k bar. And so, the vertex in the neighborhood has exactly one neighbor back, lambda neighbors in this set, and so what is the number of neighbors further? Well, this is k times. So k times k minus lambda minus 1. And counting on the other side, this is k bar times mu. Now this k bar, this is n minus k minus 1. Because 1 plus k bar is the number of all the vertices. So the graph that has these three parameters will be called strongly regular graph. And it turns out that the complement of this graph is also strongly regular. And if you're bored with my talk, then you can try homework and calculate the parameters of the complement to see what do you get. Anyway, so I did the point counting between k and k bar, so between these two sets, and I get this equation. And from this equation I can calculate n. So very often we don't put n, but if we want to be nice to the reader, we write also n. But it's really not necessary because you can calculate this n. Okay, so beside this regularity that we imposed, we can consider also the eigenvalues, so the linear algebra approach. So we define A to be adjacency matrix. So we label the vertices, so we label the columns and the rows with the vertices. So 1, 2, all the way to n, and 1, 2, all the way to n. And we put 1 in this adjacency matrix if the corresponding vertices are adjacent, and 0 otherwise. And so then the eigenvector of A is the non-zero vector, A on x, that there exists theta, the number, so that theta times x equals. Now, you can write the ith coordinate of this equation, and it turns out that on the one side, on the right side, you have just lambda times xi. On the left side, you have to sum certain. It turns out all the neighbors of I. And so this means that really eigenvector has combinatorial representation. Eigenvector is the labeling of the vertices, such labeling that at every vertex you multiply the label with the eigenvalue, and it's supposed to be sum of labels on the neighbors. Okay, so in a way you can do linear algebra, but because of this property, in a way, you still do combinatorics. But you can, of course, also try to square the adjacency matrix and use the minimality of the polynomial, and you'll find out that the strong irregular graph has exactly 3 eigenvalues. One is the valency, and to the valency corresponds the eigenvector of all ones, and multiplicity of this valency must be 1 because of the triangle inequality. And then the other 2 eigenvalues satisfy this equation that you get from this matrix equation. And once you have eigenvalues, then you can multiply, then you can calculate also the multiplicities of all the eigenvalues. So in some sense, you can define strong irregular graph also as graphs that have at most 3 distinct eigenvalues. If you have only 1 eigenvalue, you have only vertex. If you have 2 eigenvalues, you have complete graph. And once you go further from these trivial cases, then you get connected strong irregular graph. Okay, you can have still multiple copies of a complete graph, but then after that, then you have connected strong irregular graphs. So, okay, so let's think about the examples. I already mentioned complete graph. I mentioned a couple of copies of complete graph. But since I said that the complement of strong irregular graph is also strong irregular, we have immediately more examples. So, for example, if I take T parts and I join the vertices that are in different parts, I get complete multipartite graph that I denote with T times n. And I can calculate the parameters of the strong irregular graphs. So for example, in the case when n is 2, so when these independent sets have 2 vertices, this is like when couples come to the party and they want to talk with everybody else, but with who they can. So cocktail party graph. This is, for example, one example, and this example is, do you recognize the graph? Which one? Okay. So the simple things, if you want to check, if you understand these parameters, is, for example, you take 5 vertices, valency 2, no triangles, and 2 vertices at a distance 2 have 1 neighbor in common, and you get 5 cycles. You can still do, like in a couple of minutes, the case when you have 10 vertices, valency free, no triangles, and 2 non-adjacent vertices, 1 vertex in common, and you get Peterson graph. And the Peterson graph is outlined here. It's also the line graph of a complete graph on 5 vertices, and then taking the component. So this is one picture, this is another picture. This is the picture I like the most recently. Is you start with tetrahedron, you subdivide all edges, so tetrahedron has 6 edges. So you add these subdivisions. So now we have 4 vertices at the beginning and 6 additionally, so you have altogether 10 vertices. And now you join these subdivisions of opposite edges, and you get Peterson graph again. Okay, but you can continue with examples. If you, for example, take the line graph of complete graph, it turns out that this is also a Hamming graph, and you get again strong array of graphs, and these are the parameters. But in this case, surprisingly, the parameters force you only one graph, nothing else is possible. So in these small cases, you think, oh, maybe I was just lucky to get just one graph, but this is the big case, infinite family, and still only one possibility for every n. And similarly also for grid graphs, so these are the line graphs of complete bipartite graphs. They are also can be interpreted as Johnson graphs, where we take n points, we take pairs to be vertices of our graph, and 2 adjacent we intersect in 1 element. And in that case, you get Johnson graph, but this Johnson graph is the grid graph kV times kV. And again, these are the parameters, and also these parameters determine the graph precisely, except I forgot to say in both cases, we have V shouldn't be one of the values. So in this case, 4, in the upper case, 8. So in that case, you get more graphs. Okay, so you can continue, and you can go in direction of geometry. You can take designs. I don't want to introduce designs now, but if you're familiar with design theory, then you will find out that you can calculate you can make the graph out of design, and it's actually the block graph, which means that you take blocks, which are just subsets, like before in Johnson case, to be vertices, and you join 2 if they intersect, two subsets if they intersect. And what you get is strong array graph with these parameters. Now in this case, for example, you don't get uniqueness. It's not just one graph. Actually, it's completely the other way around. It turns out that if you start with this 2 design, or also called Steiner triple system, so if you choose your blocks to be free, then it turns out that well, there is just exponentially many graphs. Exponentially many graphs for every size. So it's completely different than before. Before, we had an infinite family and many, so for every size, exactly one graph. Now we have suddenly abundance of graphs. So actually, we just go to these standard triple systems, we suddenly have super exponential number of strong reliable graphs. And similarly, also if you take some other kind of design, transversal design, again you can calculate parameters. I won't define this transversal design, but it turns out that again, now you think, okay, well these are two crazy families that maybe are not important. But you'll see they actually are important, because in the case of strong reliable graph, we said we have 3 eigenvalues, and if you take the smallest eigenvalue to be minus m, and you fix this m, then you have your graph is either Steiner graph, or the block graph of transversal design, or this complete multipartite graph, or just finitely many exceptions. So now it seems that there is no way classifying the strong reliable graphs, because we have just exponentially many. But if we somehow stay away from these two families, then suddenly we have finitely many exceptions. Maybe we can attempt to do that. And that's exactly what mathematicians do. They say, well, okay, from such a relation, we get some divisibility condition, and there is more counting that you can do. Then you can prove that in certain cases the eigenvalues have to be, so if the multiplicities of both eigenvalues are distinct, then the eigenvalues have to be integral for algebraic reasons. And then you can use these integer eigenvalues to calculate the multiplicities, and you get very strong conditions. And then there are more algebra, Krein conditions, absolute bounds. I won't go into that, but they are extremely important. And you end up with such a table. So this was the first graph that we have here, although the cycle on 4 vertices is also example. But in our case, this belongs to complete bipartite graph, and kind of, we already mentioned that family, so we don't list those things. And anyway, so we have here n, k, lambda, mu, we have the eigenvalues, we have their multiplicities, and here we have the examples. And so we go and check, this case is unique, this case is unique, and so on. Okay, so here we have, first time that we have 2 graphs. Why did that happen? So it's not exponentially many and so on, but it's just 2 graphs. So the grid graph we already met, and Shirkanda graph I'll show very soon. And sometimes there is some further algebra that shows that the graph doesn't exist. But then again, sometimes you have 15 graphs, or 10 graphs, or 4 graphs, or 41 graphs. And you continue, and you say, well, when will we run into some problems? Because this, maybe we can do with computer, and people do that. But once you get to the graph on 37 vertices, there is one example. You take the finite field, convection polya, you take these to be vertices, and 2 to be adjacent if the difference is perfect square. And you get the Paley graph, and this Paley graph exists, but we don't know. Maybe there is more, nobody was able to prove. Even for such a small graph on 37 vertices, but the valence is kind of not that small. The first open case for the existence is this graph on 65 vertices. We don't know if we have any example at all. And this is, people think, a couple of thousand vertices. No, we are below 100 and we are already stuck with all the computers that we have. And Andres made the table all the way to 1,000 vertices, so you can go there and you have an infinite number of problems for all your life if you want. Okay, so the Paley graph, this was this graph where you take finite field. For example, this one can be embedded in torus, and it's locally 6 cycle. This is the TUT cage, the graph with large girth. I'll get into that later because I'll need these generous quadrangles geometries. Then we have Tepes graph, and in a way it looks like a 4 cube, but it's a little bit more complicated. And then here is the Shirkande graph. Shirkande graph seems like, again, we take a 4 cube, but then we add these dashed lines. So again, locally this graph is 6 cycle. So these neighbors, the lambda is 2, and this means that this is a cycle, and it's a 6 cycle. So actually it's a good question. If you want to start researching this field, try to go next. So try to determine all the graphs which are locally 7 cycle, or 8 cycle, and 10 cycle, and so on, and see how far you can get. Okay, so that's already bigger graph on 27 vertices, and it's already more complicated. It's hard to explain, although there is one way. Above every vertex we put 3 vertices, and somehow we built the graph out of that. So because we start with 9 vertices, we put 3 vertices above every vertex, we get 27 vertices. And so in our table, that's Schlafly, that's one of the last graphs, it's here. But I won't go into that, but important thing is it's connected with geometry. And it's also unique, you can prove uniqueness. The last kind of easy uniqueness, unless it's an infinite family. Okay, so to make life more difficult, now we started with strong irregular graphs, and if this parameter mu was different than 0, that means that any 2 vertices which were not adjacent, they had something in common. This means the diameter of the graph was 2. But, okay, start with the graph of general diameter d, and ask ourselves what is the girth of the graph. So maybe the girth of the graph is the length of the shortest cycle. Okay. And so, if you are on such a cycle, and you are here, and you look the vertex that is the furthest away, well, because the graph has diameter d, then you need at least d, at most d steps to here, and on the other side also d steps. So this girth is limited by 2d plus 1. And believe it or not, if you assume that the girth is 2d plus 1, then you can prove that the graph is already regular. It actually turns out to be a strong irregular graph. But to get to diameter 2, that's the difficult part. You have to use, you have to calculate the eigenvalues for large diameter, and that's not an easy thing. This is kind of dealing with orthogonal polynomials and such things, but people did that. Once you get to diameter 2, it's not that difficult. You need only multiplicities of eigenvalues, and it boils down to 4 possibilities. 2 we already met, C5 and Peterson graph. This one is a hard cookie, the graph on 50 vertices I mentioned here. And the last one is the graph with these parameters. And this one is still open. So this one is Hoffman-Singleton. So this one was C5. So this one is Peterson. And it's not difficult to prove. But the amazing thing is that this Hoffman-Singleton breaks into many Peterson graphs. And Peterson graph also consists of 2 5 cycles. So maybe also this graph consists of a couple of Hoffman-Singleton graphs, but nobody was able to prove. I mean, definitely this 1250 is divisible by 50. So you could maybe go this way, but nobody really knows. It's just way too difficult. Another approach in this direction is that we don't assume the maximal girth, but we assume that the graph is bipartite. Well, if it's bipartite, then we don't have such cycles, because this cycle is of odd length. So we have even length cycles, and then we have that the girth is at most 2D. And in this case, we can start playing our geometry. We have partition in two parts, and we call vertices in one part points, and in the other part lines, and we get geometry. And this geometry is called generalized polygons. It turns out that already the foregons are amazing mathematical things. Actually, three gons I didn't mention because you know them. These are projective planes. But in 4, you get generalized quadrangle. So in the case of generalized quadrangle, we have the lines have fixed size. I say that the size is, of every line is the number of points sitting on it. So s plus 1. And the size of the point is kind of dually how many lines go through that point, so it's t plus 1. And then we have an axiom that if we have a line and the point which is not in this line, that there is unique line through P that intersects L. But you can state this condition also dually, that there is a unique point on the line L that is collinear with P, which actually means that if we change lines and points, we again get generalized quadrangle, only S and P exchange. So the trivial generalized quadrangles are when one of these two parameters is 1, then we get the grid graphs and their duals. But the first non-trivial case is generalized quadrangle 2, 2, and I draw that one for you here. And yeah, if you take vertices to be points to be vertices of your graph, and you define collinearity as adjacency, you get again strong irregular graph. And this was the way how you build this Schlafly graph, for example. Okay, so there is a famous theorem of Fate and Higman who proved that the generalized quadrangles exist only for the sizes 2 that are trivial projective planes for size 3, then generalized quadrangles that I just mentioned, and then hexagons and octagons. And there was the whole book written on generalized quadrangles by Payne and Tass. Now one Belgian mathematician, Von Margegem, is working on 6 and 8, but these are difficult, very difficult things. Okay, so far my partition of vertices was just corresponding to the distance. I picked the vertex, I took the neighbors and the non-neighbors, which turned out to be vertices at the distance 2. So this was sphere 1 and sphere 2. And now I'll try to generalize this approach in the following way. I'll break the vertices into cells so that every cell induces the regular graph, and between two cells I have in a way biregular graph. So for example, if I have blue and red cell, every blue vertex has the same number of red vertices, and every red vertex has maybe different, but still the same number of blue neighbors. And so I denote this content with Cij or Cii inside the bubble, or from the other side Cji. And so I have the whole matrix of these parameters when I have equitable partition. And for example, in this case, this distance partition turned out to be equitable. Because here I had the valency here inside was lambda. The valency here, because I had mu neighbors back, and the valency k, I had then here k minus mu, the valency inside, but back I had mu, and here I had k minus 1 minus lambda. So this is that equation that I got. But we can go more general. This is, for example, one equitable partition where these axioms still hold. Notice that in every bubble I have either independent vertices or adjacent vertices, so I have regular graphs. Now, a lot of such examples of equitable partitions come from groups. If I take orbits of a group, then that gives me an equitable partition. But this is the example when we don't necessarily have an example coming from orbits. And another remark for these equitable partitions is that I use them, for example, to factorize the Toeplitz matrix, the determinant of Toeplitz matrix into smaller determinants. Another application of these equitable partitions is to search for the isomorphism of two graphs. And this is a complete problem, but Brendan McKay has a software, and this software is based on these equitable partitions. Okay, so we can generalize these strong area graphs in the following way, that we start with a graph with diameter d, and we group the vertices corresponding to the distance from a single vertex. So distance 1, distance 2, 3, 4, all the way to diameter. And I want that this partition that I get is equitable. And here I write different parameters because I have simpler situation than before. I don't have the kind of n square parameters, but I have just this line. Because if this vertex is at the distance 2, then it cannot be adjacent here. So the edges are just between consecutive bubbles. And also here I can do this counting. This times this is equal to this times this, and it goes on. So actually I can calculate, once I have these parameters bi's and ci's, I can calculate all the sizes of the bubble and then the number of vertices in the graph like before. Now, for distance level graphs, people hope that they could classify them. So given some parameter set, they want to be able to determine if they can construct the graph, or they can prove maybe even uniqueness if they already have one example, or maybe they can prove that the graph doesn't exist. And we've seen from strong area graphs, which are the distance area graphs of diameter 2, when we take connected, that actually these are difficult questions. So maybe this is even more difficult. But it turns out that maybe not necessarily for large diameter, it seems promising that we can classify them, but for small diameters, maybe as difficult as strong area graphs, maybe sometimes easier. Okay, so these are, for example, the properties of parameters. They behave like a boat. They come from a point, and then one are growing, the other one are going down, and this sequence of sizes of these bubbles is unimodal. It goes up and then down, like I said, on the edge of the boat. And there are different conditions that you can do. This is this counting thing. But you can also use these parameters to calculate the eigenvalues. Eigenvalues turn out to be eigenvalues of these three-diagonal matrix, which means that we have some kind of orthogonal polynomials in the background. And we can also use these parameters then to calculate multiplicities. They are not nice formulas, but as long as the graph is not too big, we can do it. Okay, we stay with small diameter, then for example diameter 3, then the small cycles have diameter 3, then we can generalize these Johnson and Hamming graphs there are still distance regular graphs with diameter 3. But then, somehow, for example, when you take Sylvester graph, it turns out that so the thing is, we are not dealing only with one graph. We can define on the same graph a new graph with the same points, but we choose the distance in the graph to be adjacency, say distance 2 to be adjacency, or 3, and so on. So we have all the way to diameter the number of graphs. And if they are all connected, then we say that the graph is primitive, like we were dealing with that in strong irregular case. Okay, so here is one example of primitive distance regular graph, which has funny parameters. But it turns out that it's actually equivalent to more graphs. So this means that maybe instead of studying this more graph, which has only two relations, adjacency and non-adjacency, we can go to this graph, and well, it doesn't have that many less vertices, but it has stronger structure. For example, it turns out that this graph, that the distance-free graph, is actually strong irregular, and it's actually the grid graph. So this means like we have the coordinate system, and we can there define which vertex is adjacent to which. So maybe that's the way to deal with more graphs. So how am I doing with the time? What? 10 minutes. 5 minutes. 2 minutes? Okay. Okay. So these equitable partitions, we can choose different situation. So not just distance partition, but for example, on platonic solids that were mentioned, we can take vertices that are at the maximal distance. We say antipodal vertices, and these antipodal classes in distance regular graphs also form the equitable partitions. Actually, even more. Between two classes, we have either, these antipodal classes, we have either nothing or a matching, which means that we can do the quotienting and we get much smaller graph. And that's exactly what we do in this dodecahedron case. If we identify the opposite vertices, we get the Peterson graph. And the eigenvalues, they interlace very nicely, and that factorization of the determinant of Topli's matrix actually helps you calculate the eigenvalues of the dodecahedron, which in principle can have many eigenvalues, but it turns out you just use quadratic equation to calculate. Okay, so this is the covering relation that we get in this situation of antipodal vertices, but we can generalize, so it doesn't need to be that we have only two pairs of antipodal vertices, but we can have more. And so we will define the graph to be antipodal if being at a distance diameter or 0 is actually the equivalence relation. So the important thing is transitivity in this equivalence relation. So if from vertex u we have two vertices at the maximal distance, then these two should also be at the maximal distance. And so we want that these antipodal classes are actually in this covering in the projector are actually the fibers. So the vertices that get mapped to the same thing. So which means that if we have antipodal graphs, we can calculate smaller graph. And the idea is that we try to classify first primitive distance regular graphs, and then build the graphs that are kind of above them. And so this is one case when we do this antipodal case. Now, if we stay with small diameter, then the quotient is diameter 1, the big graph is diameter 3. So we try to determine the graphs with diameter 3. And also in this case, we can build a table. And here, as a graduate student, I was able to do with a ruler to check out that there are actually two graphs. But the main result of this talk is that you can generalize this construction to this extent that you get an infinite family. So as soon as you have a graph that has a nice, it comes from nice geometry, then you can geometry a little bit less nice. Now this table goes way further, but actually here we listed n and we ordered everything corresponding to the n. But if the index of the cover is big, and that's not the right order, because maybe we should order with the number of vertices, which is r times n. And it turns out that this graph of diameter 3 is primitive and contains the smallest open case of primitive of antipodal distance regular graph. And that one is at the distance 3 from a vertex, and it has 84 vertices. So maybe I'll stop here and